What do you see up on the board right now? Two what? Okay, so two condensation trails from jets, from two planes. What do we know about those two planes, those two jets? They pass through one spot. They cross by one another. Okay, have they collided? No, they haven't collided because the contrail follows in an X pattern, right? It doesn't go kind of everywhere right in the middle here. So we have two jets. They're going pretty much perpendicular to each other. They haven't collided. They're what? Different altitudes, okay? Different altitudes. Looks like this one here is a little bit closer to the ground than this one is. Okay, different altitudes. What else do you know about them? Different times they cross, probably. Yep. This one is kind of fading out, so it looks like maybe that one passed first. Yep. Okay. Most likely two different planes. Why do you say that?
Because the jet streams are different altitudes, different times.
Okay. Okay, yeah, okay. Different altitudes, different times. Because they're different altitudes, they could very well be two different types of planes. Okay? One plane might fly at this altitude, plane might fly at another altitude. Now, that's not a for sure thing, but it's entirely possible that that's the case. I think I can even tell which way they're going. I think this one's pretty easy to tell which way it's going, right? Looks to be going this way because the condensation trail spreads out, as time goes by, right? This is the older part of the condensation trail. It spreads out a little bit. This one, I think, is going this way because it seems to be kind of spreading out a little bit up here. We just learned a lot about this picture, a lot about the composition of the sky, simply by looking at the condensation trail that follows these planes. I didn't even tell you these were planes. What was my question when we started this? What is it? What is it? You guys told me it was two planes, not one, but two planes, flying at different altitudes, crossing by one another, not colliding. Two engines, it looks like, right? Two condensation trails. Okay, one of them passed by before the other one. Okay, one's going this way, one's going this way. You guys told me a whole lot about this without ever having seen the airplanes, without ever having been told there were even airplanes there. What's the point that I'm trying to make here? We're going to study today what's inside protons and neutrons. What's inside protons and neutrons. Until today, electrons, protons, and neutrons, as far as you were concerned, were fundamental particles, as small as it can get. Electrons are still fundamental particles. And that's not just a simplification for you. As far as we know, as far as scientists know in the world today, electrons can't get any smaller. But protons and neutrons can. Now, how do we study what's inside protons and neutrons? This is great. We smash them together. We get them going at 99.999% the speed of light. We give them an incredible amount of energy. An incredible amount of energy. And then we smash them into each other. The idea is this. If these things are going really, really, really fast, and we smash them into each other, then we can overcome the strong nuclear force inside the nucleus. Okay? We can overcome that force that keeps them together. Two cars collide with each other. Okay, if they're moving fast enough, then we can overcome the force of the welds that joins the pieces of metal. We can overcome the forces of the bolts that joins this part of the car to this part of the car. We can overcome those attractive forces, and the car will break apart. And we can see what's in the car as a result of that. Okay, if we smash these protons or these neutrons into each other at really, really high speeds, then we can see what's inside them by overcoming the attractive forces that exist within them. Now, these are really small things, so we can't just watch what happens to them afterwards. Look, if we can't see a proton, then we certainly can't see physically what's inside a proton. So how do we do that? Well, there's a couple of ways. Now we use essentially digital photography, but traditionally we've used a couple of different ways, a cloud chamber and a bubble chamber. A cloud chamber consists of this chamber that has air that doesn't have any dust in it, this dust-free air that's super saturated with either water or alcohol. So in other words, it's basically ready to rain water and alcohol. Now, there's charged particles produced when these protons collide with each other. They hit each other, they smash apart, and the resulting particles that come out of this smashed up proton are charged particles. Those charged particles, not the protons, but the things that make up the protons, will ionize molecules here of this water or alcohol. So the charged particles that are coming out of the smashed up proton ionize the molecules of the water. Those ionized molecules cause the vapor, cause this gas to condense into a liquid. And what do we see? Condensation. We follow the path of this condensation trail the same way as we follow the path of two airplanes crossing by one another in the sky. If we can tell a lot of properties of those airplanes flying by one another in the sky based on their condensation trails, then we should be able to tell a lot about these particles that came from these broken up protons by watching their condensation trails. We can see their condensation trails. We can't see the particles themselves. We don't need to see the particles themselves any more than we needed to see the airplanes in that picture that I just showed you. Does that make sense? So it's kind of indirect observation, right? We can't actually see these things, but we can tell a lot about them simply by looking at the contrails that follow them. Yep. Well, optically you can, for sure. I mean, you need some sort of optical device to magnify it, but you can see it physically with the human eye. Yes, if it's magnified optically. Yeah, yeah. It's not like trying to look at a proton through a microscope. Okay, you're looking at a really, really small, thin condensation trail through an optical device. The second way we can do it is called the bubble chamber, and it's effectively the opposite of the cloud chamber. Okay, the opposite of the cloud chamber. Instead of having a dust-free air supersaturated with water and alcohol, in other words, instead of having a gas, we have a gas that's been liquefied. It's turned into a liquid. It's at a low pressure, and that lowers the boiling point of this liquid. So you've got a liquid, but it's just about ready to boil because we've lowered the pressure. Now these charged particles that come out of these smashed up protons, these pieces of fender or these pieces of wheel rims that smash off of a car that fly everywhere when a car crash happens, these little charged particles that come out of the proton when the proton is smashed up, they ionize the molecules the same as they did in the cloud chamber. But the ionized molecules don't cause the vapor to condense because we don't have vapor. We've got a liquid. It causes the liquid to boil. So in the first one, we're causing the gas to form a liquid. In the second one, we're causing the liquid to form a gas. So in the first one, we're looking at the condensation trail that follows this thing, that follows this particle that's been produced when the proton smashes apart. In the second one, we're not following the condensation trail, we're following the bubble trail. When it boils, it bubbles. We follow the bubble trail, and we get effectively the same thing. Okay, it's not the same thing. Okay, it's not a cloud that you're following, it's a bubble that you're following, but we analyze it in the same way. This is a condensation trail. You have subatomic particles that are doing crazy things. If we can introduce a magnetic field in here, hey, then these charged particles maybe will deflect in a certain direction. We change the value of the magnetic field or put an electric field in there, maybe we can determine that this particle has a bigger charge than that particle, or this particle is positive and this particle is negative, or this particle is heavier than this particle. There's a lot of things that we can determine from it simply by looking at this. Now this is a lot more complicated than this, but the same basic idea applies. Does that make sense? So what are these particles now? What are the particles that we've discovered by smashing these protons and whatever into each other? Well, there's two main kinds of particles. I'm going to write down some things here in blue, and I'm going to write down some things in red. Red is what you need to know. Okay? I want you to write it all down, but red is what you really need to know. There's two basic kinds of particles. There's the fermions and there's the bosons. Bosons are particles like photons. Okay? Like a photon is a particle, right? A boson, an example of a boson might be a photon. You guys have heard of something else, probably in the news in the last year, called the Higgs boson. Okay, the Higgs boson was hypothesized for years and years and years, but just first experimentally observed less than a year ago. It's the particle that's responsible for mass. Okay, it's what causes mass. We're not going to talk about the bosons. We're going to talk about the fermions. Fermions can be broken down into leptons and hadrons. The leptons are particles that are not mediated by the strong nuclear force. In other words, not affected whatsoever by the strong nuclear force in the nucleus. That strong nuclear attractive force has no effect on these leptons. Leptons are fundamental. They don't get any smaller. There are, as far as we know right now, 6 types of leptons. The first type of lepton is the electron. It's as small as it gets. There is also the electron neutrino. When we've been talking about neutrinos as we went through radioactive decay, that's the kind of neutrino that we're talking about, an electron neutrino. We just left off the word electron. There's the electron. There's the electron neutrino, or sometimes we just call it the neutrino. There's also a muon, which you don't need to really know, but I'm just giving you perspective here. And there's the muon neutrino. There's the tau, and there's the tau neutrino. Again, what you need to know is in red. The other stuff is just for perspective. So there's 6 of these particles here. 6 of these fundamental particles that are not mediated by the strong nuclear force that we call leptons. Plus, they're antiparticles. So the anti-electron, what's the anti-electron called? You guys know this. What's the anti-electron called? Positron. What's the anti-electron neutrino? What do we usually refer to it as? The antineutrino. Then there's the anti-muon and the anti-muon neutrino and so on, but I'm not going to worry so much about those ones. Those are fundamental and they don't get any smaller. Then we've got the hadrons that are mediated by the strong nuclear force. For example, protons and neutrons. And these hadrons are not fundamental. They are made up of quarks. There are 6 types of quarks. There is the up quark. There is the down quark. Those are the 2 kinds of quarks that we need to know because those are the 2 kinds of quarks that make up the protons and neutrons. But there are also other types of quarks. The charm quark. That's a little weird. You know what's even stranger though than the charm quark? The strange quark. Then we've got the top quark. And we've got the bottom quark. When I was in high school, when I was your age, they had observed 5 quarks. They hadn't observed the top quark. They have now. Okay, we know now that the top quark is not just a hypothesis or a theory. The top quark actually does exist. Okay, when I was in high school, it was, well, we think it should be there, we just haven't found it yet. Now they've found it. Well, we also have the antiparticles, or the antiquarks. So the anti-up, well, you'd think the anti-up would be the down, right? But it's not. There's the anti-up. We're not talking about going and playing poker here, boys. Okay, it's not the anti-up. Not anti-up as in you put your money in or put your chips in. It's the anti-up quark, the anti-down quark, the anti-charm, the anti-strange, and so on. But again, what we need to know is what's in red there. The charge of an up quark and a down quark we need to know as well, but that is on our data sheet, so we don't need to memorize it. The charge of an up quark is plus 2/3 E. Didn't we say there was an elementary charge of 1.6? Kinda. Now we're saying that these quarks can actually have a fraction of that. The down quark is negative 1/3 E. And of course, what would the anti-up quark be? If the up quark is 2/3, the anti-up quark would be negative 2/3. And the anti-down would be positive 1/3. Make sense? The final thing that we want to do here is talk about beta decay in the context now of these quarks. You can see here two reactions listed. These U's and D's represent quarks. So this would be an up quark, a down quark, and a down quark, going to an up quark, and a down quark, plus an electron, plus a anti-neutrino. Let's take a look at this. An up quark is plus 2/3. Right? A down quark is negative 1/3. A down quark is negative 1/3. What's the total charge there? 2/3, negative 1/3, negative 1/3. What is that? 0. What is a charge of 0? A neutron. An up quark is 2/3. An up quark is 2/3. A down quark is negative 1/3. What's 2/3, 2/3, and negative 1/3? It's 1. What is a charge of plus 1? This is an electron, or a beta particle, and this is an antineutrino. Isn't this beta negative decay? Didn't we say beta negative decay occurs when you have too many neutrons? What happens? A neutron changes into a proton and an electron, and then an antineutrino is kicked out. So we're now describing that beta negative decay in terms of the quarks. This is what we've done before, but now we can see exactly how it's happening. Not why, but how it's happening. The last one, up, up, down. What's that? Well, we got up, up, 2/3, 2/3, and negative 1/3. That gives me a total charge of 1. That's a proton. Up, down, down, 2/3, negative 1/3, negative 1/3.
Catherine Gray.
That's going to give me
Jeremy
0,
Kirsten Marchuk,
which is a neutron. Now this is what we call a virtual particle. It's actually kind of a two-step process. When we have beta plus decay, normally we say beta plus decay occurs when we have a proton that changes into a neutron and a positron. But what actually happens is it changes into a neutron in a virtual particle, and then that virtual particle changes into a positron and a neutrino. You don't need to worry about that. Okay, that's beyond what you need to know. Okay, you need to know that this proton changes into a neutron, and what's left? E plus is a positron, and what's this one? A neutrino. Notice they have the little subscript E there. Why do you think they're doing that now? Because it's not just a neutrino, it's an electron neutrino. We never talked about that before, right? We just called it a neutrino. Now we're calling it an electron neutrino, because we know now that there's other kinds of neutrinos. Got it? That's it.